Sorry, here we go again. So the first section is the discussion and what's been done to determine whether light is a wave or a particle. And I like this graphic because you may or may not have noticed that this spells both wave and it spells particle, which is exactly what reality is. We'll see, but it's a cool graphic, so I decided to put that in there. So this situation is actually what we call a duality. A duality is any situation in which two opposite ideas appear to be able to exist at the same time. And in this case, the opposing ideas are that there's the particle model of light, which is that light consists of tiny particles with no mass and finite energy. And the wave model of light, which says that light is a wave that propagates through space as an electromagnetic wave that can have varying wavelengths, frequencies, and other characteristics, as we'll see. And we're going to look at the behaviors of light to see which are consistent with the two different models. And the behaviors of waves that we're going to look at are diffraction, interference, polarization, reflection at surfaces, refraction at boundaries, and Doppler shifting of frequencies. And then we're going to examine the photoelectric effect, which occurs only for particles, not for waves. And you will see that light evidences all of these behaviors. So there's no real way to say it is a wave or a particle. It is a duality, as we'll see. So the photoelectric effect was actually demonstrated by Einstein, for which he actually was awarded the Nobel Prize in 1921. And the photoelectric effect occurs when light strikes a metal surface and an electron is ejected. So here's light, incident light coming into a metal surface, and here's they call it a photoelectron in this image, but it's an electron that gets ejected out. And Einstein showed that the kinetic energy of this electron depends only on the frequency of light, not on the intensity, and that increase the number of photons hitting the surface by increasing the intensity has no effect whatsoever on the kinetic energy of the electrons. And again, he was awarded the Nobel Prize for this observation. And the wave model can't explain these aspects of the photoelectric effect. First of all, instantaneous emission. Electrons are ejected almost as soon as the light hits it. And in wave theory, energy would need, with the wave hitting the piece of metal, energy would need time to spread out and build up before an electron could be ejected. And the fact that the electron is ejected almost as soon as the light hits it says that the light is a single particle that transfers all of its energy instantaneously to some electron, which is then ejected. Again, consistent with the particle theory of light. A second characteristic of the photoelectric effect is called threshold frequency. That below a specific threshold, a frequency, no electrons are ejected regardless of the light's intensity. So if the light is below a certain frequency, there's no matter how long, no matter how intense you make the light, you can't eject any electrons. And this again aligns with the particle model. And then the final characteristic is that the fact that the ejected electrons depend on frequency and not intensity. The maximum kinetic energy of electrons that are measured as they exit this metal depends specifically on the frequency of the light. The particle model explains this, but the wave model can't. So these three characteristics of the photoelectric effect seem to demonstrate that light is acting like a particle and not a wave. And in fact, Einstein left this experiment concluding that light must be a particle. Little did he know, or he probably did know, but there are also wave behaviors that are consistent with light. So many of us know many of these behaviors, but diffraction is light bending around barriers as it passes through openings. That's diffraction of light. Polarization means that waves of light and other electromagnetic radiation acquire a specific orientation of their oscillations and become polarized. So we'll see what an electromagnetic wave looks at and how that can be oriented. But we're all familiar with polarized light through sunglasses and other kinds of reflective things. Reflection is the abrupt change in direction of a wave when it strikes a boundary between different media and bounces back into the original medium. Refraction is a change in direction and speed of light or waves as they pass through a boundary between media of different densities. Doppler shifting is the lengthening of a wave if it's being emitted by a source that's moving away from the observer, whereas and that's called a redshift. Wavelength from a source that's moving towards the observer shortens, and that's called a blue shift. We'll see how that's used in various observations. And finally, interference is a really important one, that two or more coherent waves, and I've got a really long definition of coherence here, but I'm not going to go into that because this is the first of many different rabbit holes we could disappear down into tonight. But suffice it to say that the coherent waves possess exactly the same frequency and maintain a constant phase relationship to each other over time. That's all I'll say about it. But two or more coherent waves, if superimposed, when traveling through the same medium, result in a new wave pattern with either higher or lower amplitude. Constructive interference results in a wave of higher amplitude, and destructive interference results in a wave of lower amplitude. So to demonstrate this, so this is a graphic of wave interference. So these are two waves that are traveling in the same direction. They're synchronized in that each point on each wave occurs at the same place throughout the wave. And if you superimpose these waves on each other, then the peaks superimpose to create higher peaks. That's constructive interference, and higher lows. That's constructive interference. And if they're offset each other by exactly half a wavelength, then then you get destructive interference. It means that these cancel each other out. So constructive and destructive interference. These are going to be very important when we look at the data that suggests that light can also act like a wave. A standing wave is formed by perfectly timed interference of two waves passing in different directions. So if you have simultaneous waves entering from the right and entering from the left, they will become standing, and as in this diagram here. So this wave is going in this direction, this wave is going in this direction, and if this wave is emitted here and keeps bouncing back as it goes back and forth, eventually becomes a standing wave that represents the superimposition of these two waves. And this is an example of a standing wave. So, and standing waves have nodes and antinodes. Nodes in a standing wave pattern that appear to be standing still are called nodes. So it's a little hard to observe, but I'm going to put my cursor right over that node, and you'll see that however wildly the wave appears to be moving, the part of the wave that's covered by that cursor is not moving. Ditto with here, here, and every node. The antinodes are points that undergo maximum displacement during each vibrational cycle of a standing wave. So here is the antinode, another antinode. So these are points of maximum energy, and these are points of minimum energy in a standing wave. And we're going to use that towards the end of the talk when we actually learn how we can measure the speed of light in our kitchens. So the double slit experiment uses interference and refraction to show that light acts like a wave. So Thomas Young did this experiment in 1801, and the experiment consists of using a coherent light source to illuminate a plate that has two parallel slits in it. The light then passes through the two slits and impacts a screen on the other side that documents it. The wave nature of light causes the waves passing through the slits to diffract and then to interfere with each other, producing light and dark bands on the screen. Only wave theory explains this behavior. So in this is the diagram of the double slit experiment. So this is the source of the coherent light. This is slit 1 and slit 2. Now, if this coherent light consists of multiple particles, then the particles would each pass through, impact on the screen back here, and you'd get two heavily lit patterns here, but nothing anywhere else. As a wave, however, as it passes through the slit, it gets diffracted in various settings. And so these two slits result in two waves that interfere with each other. And the interference pattern, these red lines here are the antinodes, and these black lines here are the nodes of minimum. So these the pattern here produces a maximum line here, another maximum line here, and the nodes, the minimums, produce no color. And so this definitively shows that in this case, this coherent light, which can be produced by a laser or any number of different sources, lasers are usually what people use, definitively shows that light can act like a wave as well as acting like a particle. So the answer to the question is actually, it's a duality. And if this feels confusing, well, welcome to quantum mechanics. This is just the first point of confusion that, for me at least, quantum mechanics gives rise to. But it is a duality. If people ask you whether a light is a wave or a particle, then the answer is both. That at times it can act like a particle, and at times it can act like a wave. So here's particles passing through a slit, and here's light passing through and diffracting as a wave. So the next topic we're going to take on is the fact that light can have momentum. And this was very counterintuitive to people. Nobody really understood this. How can a particle without mass, by definition a photon has no mass, have momentum? And I'm going to show you a demonstration of this if you've never seen this before. So this is from YouTube. I'm hoping this works. I have to turn off my cursor. Okay, and here, this is the vacuum. This guy's shining a laser on this little mobile, and just the impact of the light is causing this thing to rotate. And the more he shines it, the faster it rotates. So that documents that photons can exert force, and therefore they have momentum. So you can demonstrate this by math. Now, I'm a big critic of people who have too many equal signs and equations in their talks. Our general rule is that we should have less than 5. I think I do that here if you only count 1 per slide. But in this case, you'll recognize that this equation actually contains E equals mc squared. And it turns out that E equals mc squared is a special instance of this general equation that applies only to objects with mass that are not moving. So E equals mc squared only applies to objects that have mass and are not moving. The more general equation factors in momentum. So in here, the energy squared equals momentum, which is the P times the speed of light, quantity squared, plus the mass times the speed of light, quantity squared. And you can solve this equation to E equals momentum times the speed of light. So as applied to photons, which are massless, it shows that photons can have momentum even though they don't have mass. So we've seen the both practical demonstration of that in the YouTube video and the mathematical demonstration of that in this slide. And this is by a really cool, if you want to take a look at it, a very cool video on the Fermilab website in YouTube. So we're going to go on to the electromagnetic spectrum at this point. So there are four forces in the universe that we know of right now, and this slide is the only time I'm going to really allude to any of these forces. But the strong force is the glue holding atomic nuclei together. It's mediated by gluons and quarks together with nucleons. It overcomes the electromagnetic repulsion between protons. So the strong force is what keeps protons in the nucleus, because otherwise they're the only positive, they're the only charges in there. Neutrons have no charge, so this is what keeps them in the nucleus. The weak force is responsible for particle decay and nuclear fusion in stars, and they're mediated by W and Z bosons, and these are literally the only two things I know about the weak force. I'm not prepared to discuss that in any great deal tonight. And then there's gravity. The gravitational force is a third force. But what we're going to spend some time on is the electromagnetic force. And the electromagnetic force is generated by vibrating electric or magnetic charges that propagate perpendicular to each other. So this is an electromagnetic wave. And it can be generated either by this B stands for magnetism. So this is the magnetic wave, and this is the electric wave. And you can start out with a magnetic wave and produce an electric wave to match, or you can start out with an electric wave and produce a magnetic wave. And the two together are an electromagnetic wave. So we know how to do this, right? We know that if you wrap an iron nail in copper wire and run a current through that copper wire, the iron nail will become magnetic. Similarly, if you move a magnet up and down a coil of wire, you'll generate an electric current. So we know how to do this practically, and this demonstrates that as a reaction to this electric force moving, we generate a magnetic force, and vice versa. The electromagnetic force can propagate through solids, liquids, and gases, but no medium is required. For a long time, people thought that light needed a medium, the electromagnetic force they could observe. But these electromagnetic waves propagate fine in a complete vacuum, and there's no undetected or hidden medium that allows them to propagate. They don't require any medium whatsoever. So these are a couple different examples of the electromagnetic spectrum. In these cases, the slower electromagnetic waves are on the left, and the faster ones, the ones with higher wavelength, are on the right. So the slowest electromagnetic waves we usually deal with are radio waves. And then our microwave ovens are slightly higher frequency than radio waves. Then infrared waves below red. The light spectrum is a relatively small but important part of the electromagnetic spectrum in here. And this, as we'll see when we get to using prisms, can be broken down into the visible spectrum. Ultraviolet is next. Then X-rays are higher frequency, and the highest frequency are gamma rays. And each of these have their use in various different, so we know what radio waves do. We use microwaves probably almost every day. X-rays can be used both diagnostically and therapeutically, and gamma rays can be the same. And we're going to spend the rest of the talk, or at least this part of the talk, demonstrating how we use the visible spectrum. Here again, this again renames them in a little more visible way, but it points out that this is a logarithmic scale. So radio waves can have a frequency of 10, as low as 10, but gamma rays are 10 to the 20th, 10 to the 22nd, 10 to the 24th. So each of these steps is a logarithmic step. So these, and since we'll see in a little bit that the frequency is directly related to the energy, the higher the frequency, the higher the energy. Gamma rays are many orders of magnitude higher frequency and more energetic than radio waves and anything that comes before them. And then this actually comes from explaining to patients on the CDC website about how these higher energy waves are used to improve health. So properties of electromagnetic waves include frequency, how many waves go past a given point per time. So if this is 1 second, then 1, 2, the frequency is 2. So, and the number of waves that pass by a given point per second is equal to hertz. So most of us are used to dealing with like megahertz or kilohertz when talking about radio waves and different things. But the basic unit that was defined by Hertz himself, I believe, is the number of waves per second. The wavelength is the distance between any 2 points that are in phase with each other. And points that are in phase with each other are any 2 points on this continuum. So all the ones that are at the top, all the ones that are at the bottom are in phase with each other. Any of the ones that are crossing the resting line, it's called, or anything in between, as long as they're on the same point in that curve, they're said to be in phase with each other. So the wavelength, although we typically measure it from peak to peak or trough to trough, if any 2 points in this curve that are in phase and so you'll see that in here. So here, this is an 2 nodes, so it's from node to node here. The amplitude is the height of the wave above the resting point. So this is the resting line, and this is the amplitude. Velocity is interesting. In a vacuum, all electromagnetic waves travel at the speed of light. So V, which is stands in this case for velocity. V is used for a couple different terms in this talk, so I'll apologize for that in advance. But in a vacuum, all electromagnetic waves, and in any other medium, they all travel at the same speed, even though it may be slower than the speed of light. Velocity is completely independent of frequency. And so this is the equation that relates frequency to wavelength and velocity. And you'll see here that since velocity is a constant in any given medium, that frequency and wavelength are therefore inversely associated or inversely related. The higher this goes, the lower this has to be. So if you want high frequency, you have lower wavelength, etc. Energy of wavelengths, in general, the shorter the wavelength, the higher the energy. Here's another equal sign, so you can credit me with 2 now. The energy of a given wave is equal to Planck, who is a well-known physicist, times the frequency. So you'll see that energy is directly related to the frequency. And in this particular graphic, the low wavelength waves or low frequency waves are to the right rather than previous. But so these are lower energy to higher energy. And within the visible spectrum, red is lower energy than blue and violet on the other end here, because it's a longer wavelength or higher frequency or shorter frequency. So now that we know about the electromagnetic spectrum, we're going to take a look at spectroscopy and how it informs what we know about light. So spectroscopy is defined as the study of how matter interacts with light, how it affects light passing through it, going around it, emanating from it. And most of what scientists know about the cosmos comes from the study of light. If you look at any study or anybody reporting something we know about the universe, the cosmos, most of it, all of it in some respects, is built on spectroscopic analysis of light coming from that part of the universe or those bodies or those. It's a hugely important thing, and one of the reasons why I really wanted to give this talk, because so much of what we know about the universe is built on spectroscopic analysis of light coming to us. Phil Plait is one of my favorite astronomer writers. Says, light is the ultimate cosmic messenger. Every piece of information we have gathered about the cosmos, from the birth of stars and the presence of black holes to the chemical makeup of exoplanets and the age of the universe, comes to us on the wings of ancient photons. I love this quote. So, white light is composed of all color wavelengths, from the near ultraviolet to the near infrared. And when passed through a prism, we create a spectrum. So shorter, more energetic wavelengths are bent more by glass in this case, or some sort of crystal. And less energetic waves are bent less, which spreads them out. So in this case, light's passing through two boundaries, here and here. And in one case, the red is bent a little bit, and then it's bent a little more, but the blue and the violet are bent more here and even more here. And if we put some sort of screen up here or some sort of detector, we'll see a spectrum. And if this is truly white sunlight, then we'll see the spectrum fully from red to violet. And the way our understanding of what happens in the universe comes from our looking into, as light is emitted by or passes through objects, which of these is either present or absent in the spectra that we see. And we'll see that atoms, again, I don't think to tell anybody this, but just remind us, atoms consist of nuclei and electrons. So here's a cartoony picture of an atom. This is the nucleus here. And the important thing as far as the spectra are concerned are that the electrons don't exist in a big cloud or randomly going around. This is incredibly more complicated than I'm explaining it. But in general, electrons have different levels they can be at in any given type of element or atom. So in this case, for this element, whatever it might be, the resting state of the electron is right here, and this is a higher energetic state, yet another higher energetic state, and the highest energetic state. And is as if the electron absorbs energy, it can move from one state to the next, but it can't move in between states. It has to move from one state to the next, or if it drops down a state, it can do so by emitting a photon, getting rid of just enough energy in that photon to go down from 8 to 2 or 10 to 2 or 32 to 8. So this, all the different combinations of jumps and decreases account for different photons either being emitted when it decreases or emitted when it absorbed when it jumps up. So as light shines through this, only certain wavelengths of light, only certain types of photons are going to be absorbed. And if after the light passes through, as these photons lose their energy, they will emit a spectrum that will show the same thing. So this is another picture of, excuse me, what we call absorption and emission spectrum. So in absorption, as I just said, electrons move from a lower state to a higher state of energy. And during emission, electrons move from a higher state to a lower state. So in this case, we're looking at one electron in its ground state. It absorbs a photon of just sufficient energy to boost it up to this excited state, and it lives there. And if you shined white light through here, it would absorb only that wavelength of light. That would be exactly what it needed to get from here to here. And in this case, probably here to here. Well, some of the electrons would absorb that. So if you looked at a spectrum of light passing through a gas or something of these elements, then you'd see a complete spectrum except for the two wavelengths that are absorbed by these atoms. So again, absorption and emission. If you you excite all the atoms in this gas by a powerful white light showing through it, and then turn the light off, and then get a spectrum of the emission of that, then you will see all the atoms that are doing this, so that you, rather than seeing the missing quanta of photons, you'll see the present photons, and we'll see examples of that in a little bit. I'm going to harken back for just a second to see this is how the photoelectric effect occurs in a way, and this shows X-rays doing it, but when Einstein was doing this experiment, they didn't know about X-rays. So, but in this case, the photoelectric occurs because the incident light or electromagnetic radiation is so strong that it doesn't just bump these up to higher levels; it bumps it completely out of the atom. So an ejected electron is seen with the photoelectric effect. So specific spectra. So as I've been hinting at, specific elements or molecules absorb or emit light at characteristic wavelengths according to their electron configuration. And this is referred to as their spectroscopic fingerprint. I've already talked about absorption and emission spectrum. A continuous spectrum is simply light produced by a hot, dense source like our sun that has all the wavelengths, all the visible wavelengths in it. And an absorption spectrum consists of blank spots in the spectrum where white light passing through the object, those wavelengths were absorbed by the specific electron configuration of that element or molecule. And an emission spectrum is exactly the opposite, that if light is emitted by an object, then the bright lights in the spectrum that are seen are representative of the same electron. You'll see that the bright lights emitted in an electron spectrum for the same element correspond exactly to the blank spots in an absorption spectrum. We'll see that in just a few minutes. So here is another example. So a hot black body, a black body, I think there's a show actually called Black Body something, but a black body, just to define it, is an idealized object that absorbs all electromagnetic radiation that falls on it, regardless of the frequency, and reflects nothing. And then it also emits radiation based solely on its temperature, as defined as a black body. So our sun, by and large, can be defined as a black body, and most stars can be. So if this black body is emitting white light, and that white light passes through a cloud of a cooler gas, let's say helium or hydrogen or oxygen, and then we separate that gas with a prism into a spectrum, we'll see absorption lines. And these absorption lines, each one of these corresponds to a specific electron jumping up to a specific level in that cloud of gas. So that's the absorption spectrum emitted by white light, pure white light from this black body coming through the cooler gas. And if we somehow block this light from this cloud of gas after it's heated up or excited by these all this radiation coming from the black body, eventually these electrons will emit the added energy, and their electrons will go back to their resting state, and they will emit them in the same quanta that they absorb them in. So here's the emission line spectrum, and you'll see that what is emitted corresponds exactly to what is absorbed by these lines. So these both can be used in similar ways, depending how the light arrives at you or what you do to it. You can use either one of these, but they both give you very similar information. So this is a spectrum of hydrogen gas. This is the absorption spectrum. And these hydrogen, as we know, only has one electron. So each electron, this electron has 1, 2, 3, 4 levels it can go to. And these are higher, lower, lower, and lowest level. And this is an emission spectrum for hydrogen gas, again, corresponding to exactly the same wavelengths that are absorbed when white light is shined through it. So we said that we've learned everything we know about the universe, almost everything, from spectra. So what specifically can we learn from spectra, and how do we learn it? So temperature can be measured by spectra. So a black body radiation curve is a spot of spectral intensity, emitted power per unit area per wavelength against wavelength. And these are examples of two spectral curves. And it turns out that the peak radiation is dependent. These peaks are dependent solely on the temperature of the body that's emitting the wave. So they've got a black body. You don't get any extraneous radiation from reflection or anything. This is all what it's producing. And so a black body that's emitting this radiation curve would be 5,500 degrees Kelvin. And a body that's emitting this curve, the peak, is at 4,500 degrees Kelvin. So what can we do with this? Well, we can come up with what's called the spectral classification of stars. So we know that based on the spectrum, the stars have been divided into 7 different classes, each with their own subclasses. But the most energetic class are the blue stars, and they have spectral curves that say that they're burning at 30,000 degrees Kelvin. B class, which are blue-white stars, are 20 to 30 degrees thousand degrees Kelvin. Our own sun is a G class star, burning at 5,200 to 6,000. At least the surface temperatures are degrees Kelvin, and this is again a pictorial representation of these. And we can actually, we don't need a spectrograph to determine this. We can, with telescopes, we can see that stars are bluish or reddish or yellowish. So we can see these in fact, it's fun looking at double stars because often they're different wavelengths or different temperatures. And so we can see a blue one coupled with an orange one. And this has been a very important discovery and use of this. We can also learn from spectral analysis composition. So the elements present in stars, novas, etc. If they're glowing, then we can analyze the emission spectra of them. If they're just gases that are in between us and a star, by assuming the star is emitting mostly light as a black body, then we can examine the absorption spectra. And this obviously gets incredibly complicated with the multiple elements and multiple electron levels, and something is both a lot of spectra are both emission and but in general, this is the idea. We can discover the composition of various deep sky elements. Actually, the density can infer that in ways that I don't fully understand. When a very dense object causes the spectral lines to become fuzzy. And this fuzziness can be quantized and converted into a measure of how dense the object is that we're looking at. It can also be determined, velocity and direction of motion can also be determined. So objects that are moving toward us cause blue shifting. Objects that are moving away from us cause red shifting. And it, all other angles between directly at us and directly away from us cause various degrees of shifting. So they can allow us to do that, to determine velocity and direction of motion. Distance can also be determined by using spectra. So using the cosmological redshift and the Hubble constant, we can determine how far objects are from us by up to a billion light years. So this is an object much further away, and moving away from us, causing a much bigger redshift than this object, which is actually moving towards us, causing a blue shift. We can also, believe it or not, we can also determine rotational velocity. So if a star is rotating, or a body is rotating that's emitting light, if we're looking at it from this perspective, the top half of that star is rotating away from us, causing a redshift. And the bottom half is actually rotating towards us, causing a blue shift. So the absorption spectra for this star then would be, if that's our exact perspective, it actually broadens each absorption line. So this is one with no rotational velocity. This is the red shift added. This is the blue shift added. And these summarized together just cause, and they can interpret the degree of broadening as rotational velocity. It's unbelievable to me that even with the powerful telescopes we've got, stars still look like points of, little pinpoints of light. We can still see enough of the light to determine light that's going away from us and the other side of the star coming towards us. That's just mind-blowing to me. All right, so that tells us about spectra and what we can do to investigate the universe from it. The last topic I'm going to address tonight is the speed of light. How we got there, how we determined what it was, and some pretty cool things about it that we're going to talk about right at the end of the talk. So the speed of light, which is defined as c or labeled as c, is 186,282.4 multiple or digits miles per second. Or an easier way to remember it is it's roughly 300,000 kilometers per second. And this is in a vacuum. So if it's going through denser media, it'll slow down some. But in a vacuum, these are the speeds of light. And a light year is how far light travels in a year, a light minute, how far it travels in a minute. Second, these are measures of distance and not time, which are sometimes confused. This is a graphic I got from a Facebook post that asked the question, what if you traveled at light speed, the shocking travel time? So it takes light 1.3 seconds to go from Earth to the moon, 12 minutes to go from the Earth to Mars, 5 hours, 5.5 hours to go to Pluto, Proxima Centauri, Proxima Centauri is 4.2 years, and the center of the Milky Way is 26,000 years away from us. So light travel, I mixed up though. The observable universe is 46 billion years. So light's been traveling that long, 46 billion years before it hits our eyeballs. So when you're looking at things like Proxima Centauri or distant stars, the photons that are hitting your eyeball started that far away. However, this says, what if you traveled at the speed of light? And we're going to find out in the next few slides that if you were traveling at the speed of light, actually time would stop occurring. And that's called a relativistic effect. And that's called time dilation. And as you approach the speed of light time becomes infinitely slow until if you were ever able to reach the speed of light, time would actually stop relative to a non-moving observer or relational object. So this is a misleading question. So if you could travel at the speed of light, time would cease to be occurring for you. And we'll see why that happens in a minute. So the history of the speed of light, people before it could be measured, were wondering whether light had any speed at all. So Aristotle argued that because light travels instantly, it must have infinite speed. There's no detectable lag between lighting a match, or not that Aristotle meant, lighting a candle or a lantern or a fire in Aristotle's time. Light does not perceptibly take a while to get to you. So at the distances Aristotle had to deal with. So Empedocles argued that since it travels, light has to have a finite speed. And an Arabic scientist proposed that light travels from objects to our eyes and therefore must travel at finite speed, similar to this argument. So people weren't even sure that light had a speed. So, and then in the 1600s, people started doing time of flight experiments. And these are basically experiments that measure how long it takes between a light being lit and someone who is some distance away being able to see it. So Isaac Beckman in 1629 asked an observer if there was a difference when light was when light was observed from mirrors of differing distance. So he would ask somebody to shine a light at mirrors that were a differing distance apart, and if light had a finite speed, then theoretically at least the distant mirror should show the light after the closer mirror. But he was using hilltops as opposed to miles away or thousands of miles away. So although there was a slight unmeasurable difference in how long it took the light to get to the more distant mirror, it was unobservable from his perspective with the measurement tools he had. At around the same period of time, Galileo constructed an experiment where one observer uncovered one lantern, and a second observer several miles away from that observer, as soon as he saw the light from the first observer, uncovered his lantern. And again, even though the distance here was several miles away, there was no observed difference. And that's because light is moving much faster than we can perceive it in this case. But they're all getting at the fact that there should be a difference in distance. Later on in the 1600s, Ole Romer used Jupiter's moon Io to measure the speed of light. So these are getting further away. So he observed that eclipses by Jupiter of its moon, so Io would pass behind the moon, and then it would appear on the other side of Jupiter at some point. And he noticed that light from eclipses arrived earlier when the Earth was closest to Jupiter than when the Earth was when Jupiter was on the far side of the sun. So when Jupiter was on the same side of the sun as Earth, the eclipses arrived much earlier than when it was more distant. And Romer measured the time difference between Io's emergence when Earth was closest and furthest from Jupiter, and found that there was a difference of 22 minutes in how long it took the light to get to us. And it turns out that the actual measured number since then is 15 minutes. He didn't actually calculate the speed of light, but he sent his data to another astronomer, Christian Huygens, who calculated light speed as 212,400 kilometers per second. Remember, the real value is 300 or slightly less than 300, and 132 miles per second. But they're getting in the ballpark. They're getting in the ballpark here. Edmund Halley, a famous astronomer that we know about, again, I mean, this work's all being done in the 1600s, mathematically refined. He didn't repeat the work, but he refined and republished Romer's work. And his calculation using Io's eclipses by Jupiter came to 186,000 miles per second, or 300,000 kilometers per second, which is only 0.1% off the currently accepted value. So in the late 1600s, they were coming within a tenth of a percentage point of the real values of the speed of light. Not bad. So then there became the cavity resonance method started being used, and this measures the speed of light by determining the resonant frequency, and weight. And this is another use for the letter V here, and wavelength of microwaves inside a precise metal cavity. So the resonant frequency is the natural rate at which a system vibrates when it's a standing wave. So he measured microwaves that were in a box, measured their wavelength and their frequency, and then from this equation, light spin, and assuming that the light was traveling at the speed of light, these microwaves are traveling at the speed of light, which is close to being true, he could calculate the speed of light by multiplying the wavelength and the frequency. The wavelength he knew and the frequency he calculated. And he was incredibly close, within 50 meters per second of the accepted value. So these were in the mid 1900s. Now it turns out that you can measure the speed of light with a microwave and chocolate or cheese. You can do it. You can do a cavity resonance experiment in your kitchen, and this is how to do it. Remove the turntable from the microwave. Put a layer of chocolate or American cheese slices on a plate, hopefully a level plate, or some sort of metal plate, or a ceramic plate. Put the plate on the center, and then turn it on the microwave for 30 seconds. And without the revolution, standing microwaves will be set up in the microwave when this happens. And so there'll be antinodes that maximize the effect of the energy of that standing wave, and the where these antinodes occur in the standing wave in the cheese or the melty bits will start to melt before the rest of the cheese does. So if you 30 seconds, or you experiment with it, do it a little more, a little less, you want to interrupt the process when there are little points of melted cheese or chocolate that you can measure the centers between. So you take the center of two melty bits as best as possible, and you measure that distance, and this distance is half a wavelength. Remember, a wavelength ends up being 2 antinodes. So you multiply that to get a full wavelength. You convert it to meters, and then on the back of the microwave, it'll give you the frequency in megahertz of the microwaves that it's producing. Convert that to hertz. 1 megahertz equals 10 to the 6 hertz. And then multiply the frequency in hertz by the wavelength in meters to get speed of the microwave in millimeters per second. So in the YouTube video that I watch, and I can give you guys the URL for this, the guy calculated the speed of light using this method, only 0.3% off what a true value. So we could do this using the microwave at Farish, and I'm really psyched to do this. I will put up for the chocolate or the cheese or both, and we can have and then after we measure the speed of light at Farish, we can have a fondue party and use the fully melted chocolate and cheese. But this is a very cool thing. We can do this ourselves. All right, the final method for measuring the speed of light is called the interferometry method. And an interferometer, this is it measures the point of light is a laser. It has to be a coherent point of light. And this light is split into two beams, one allowed to pass through to that detector or that mirror, another split and allowed to pass to that mirror. And then they both are reflected, and this is reflected off this side, that passes through, and there's a detector here. And if these mirrors are the same distance, then the waves don't really they experience constructive interference. But if you move one of these mirrors back and forth, it'll cause constructive or destructive interference, and there'll be a very specific interference pattern. And this interference pattern allows precise calculation of the wavelength of this light. And again, if you have wavelength and you have frequency, you can calculate the speed of light. So, this image comes from LIGO, which is one of the huge interferometers that's currently detecting gravity waves and things like that. So, let's see if there's another. So, this resulted in estimates of the speed of light that were so accurate that we'll see later they began using it as a standard. So it turns out that way before these earlier guys used this method, Michelson-Morley attempted to prove that this was still when they were arguing about whether some sort of medium needed to be present for light to travel. So he attempted to prove that a medium was required. He hypothesized that light that passed through more easily the ether than a similar beam at 90 degrees. So one of these, I don't know what he actually did to make the ether, but one of these had ether and one of these had a vacuum. And he hypothesized that without the ether, the vacuum, this light couldn't travel. And he found that there was, or would be impaired. He found that there was no difference between the two limbs. And so he thought that his experiment failed, but in fact, this was the first interferometry method experiment ever done. So people describe this as one of the most famous failed experiments in history. He invented the method of interferometry to prove a point that wasn't true, but he got credit. All right, so this is how. So now I'm going to finish with just a bunch of fun facts about the speed of light. So it turns out that we are now using the speed of light to define a meter. So the 17th General Conference on Weights and Measures, held in Paris in 1983, decided to define the meter according to the speed of light rather than defining the speed of light according to the meter. So the speed of light was set precisely to this number through interferometry, and then the meter was defined as, and this is meters per second now, as the length of the path traveled by light in a vacuum during a time interval of 1 over that fraction of a second. So meter now is defined by the speed of light rather than the speed of light being defined by meters. Next fun fact. Experiments show that early expansion of the universe was actually faster than the speed of light. So we know that one of the rules of the universe, one of the universal laws of physics, is that nothing can travel faster than the speed of light. Nothing. So how can these experiments, which are quite robust, show that the early expansion of the universe was faster than the speed of light? And the reason is that it was space-time itself that was expanding, not matter. So it wasn't light that was moving away from us. It was space-time itself. And so the speed of light limit didn't apply to space-time itself. As evidence of this, so any given element should have a unique fingerprint, right? So, but they've got evidence now that atoms of a particular element on Earth and atoms of the same element in quasars that are about 10 million billion years old emit different wavelengths of light. And this can only become there, and they're only be because they are moving. This light was emitted when that part of the universe was still traveling faster than the speed of light. Time dilation, I think, is the one of the most fun speed of light facts. Although I I broke my mind several times on trying to understand this equation this week, but and I've mentioned this earlier. When objects move close to the speed of light, time itself slows down relative to slower or non-moving observers. And the equation that shows this, or the equation that describes this is time measured, time is experienced by a stationary observer. This is time as experienced by an observer in the moving object or in the moving object's frame of reference. And that is all multiplied by something called the Lorentz factor, or abbreviated as gamma. And you'll see that it has the velocity of the object and the speed of light. So these terms are both determined only by the relationship between how fast this object is moving in comparison to the speed of light. And this is 1 divided by the quantity, the square root of 1 by this ratio squared. So because v can never exceed the speed of light, this ratio will always be a fraction between 0 and 1. So at everyday speeds, v is incredibly smaller than c. So when v was vanishingly small, this becomes close to 0, and then this whole term becomes 1 over 1. So it becomes nothing. It becomes 1, and that means that time is experienced at whatever speed you're talking about is essentially the same as time experienced by the stationary observer. However, as v increases, the Lorentz factor begins increasing away from 1, higher than 1. And at objects that are traveling at 86.6% the speed of light, so here v equals 0.866 c, the Lorentz factor actually ends up being 2. So time is experienced by, so if you think of time as experienced by the stationary observer, if 1 hour passes by for this guy, with the Lorentz factor being 2, 2 hours pass for this guy. So in the same, for the person moving at 0.866 the speed of light, time passes twice as slowly as it does for the stationary observer. So it becomes important as you approach the speed of light. As v actually approaches c, it causes the Lorentz factor to approach infinity. So when this factor, because it ends up being 1 over 0, so which is infinite or undefined. So that means actually that for an object moving at the speed of light, so in his case, v equals c, time theoretically stands still. So as I said with the one slide I showed right at the beginning of the speed of light talk, if anybody asks you what the how fast you can move, or how long it takes to get somewhere moving at the speed of light, the correct answer is that it's unmeasurable because time does not pass if you're moving at the speed of light, which, as we know, is impossible, but it's a fun thought experiment to do. And it turns out this Lorentz factor is important in a bunch of different quantum mechanics stuff, including time dilation from gravity that we're going to talk about in 2 seconds, or at least just mention. So as examples, and these are experimental results. So at least mathematical results. So at 80% the speed of light, clocks would move 60% slower than they move when somebody's motionless. For an observer on a spaceship moving at 0.9% the speed of light, that person would see time moving 2.3 times slower than an observer on Earth. This has been confirmed actually by doing very careful aircraft clock experiments with very fast aircraft that reproduce exactly the slowdown. They show that aircraft that are taken to high speeds, actually the clocks on those aircraft slow down imperceptibly for us, but measurably slow down compared to clocks on Earth that aren't moving. This has been shown in multiple experiments. Another way we actually know this is through the GPS system. You know, the satellites that are circulating that enable us to know our position on Earth. So the GPS satellites travel at about 14,000 kilometers per hour. Time dilation at that speed causes their onboard clocks to tick slower due to velocity-based time dilation. But at the same time, these satellites are so high that it should gravity also causes time dilation, and the higher the gravity, the more time dilates. So whereas the speed causes time to pass slower for these satellites, the fact that they're not at the surface of the Earth and experiencing weaker gravity speeds up their clocks. So we've got two relativistic effects here due to time and gravity. So it turns out that GPS clocks lose about 7 microseconds per day from their orbital speed, but they gain roughly 45 microseconds per day from the lower gravity. The net effect is that they gain 38 microseconds per day, and without relative, this seems small, but without relative fixes, the errors caused by these gains and this gain of time would exceed 10 kilometers annually, meaning that by the end of a year, your GPS position, as calculated from satellites that weren't being corrected for relativistic effects, would be 10 kilometers off. And I was talking about this one time at a observing event at Farish, and one of the guys who was there actually was part of NASA when they were launching the GPS satellites. And he remembers a discussion whether the clocks, whether they needed to use Newtonian time or relativistic time on the GPS satellites. And they demonstrated using this reasoning that they had to be relativistic time, because if they didn't correct for these gains in microseconds, they would lose their accuracy very rapidly over time. All right, so kind of to summarize for this session, part one, we talked about the fact that light, it's a duality. Light behaves as both a particle and a wave. That light has momentum, even though photons have momentum, even though they don't have mass. That an electromagnetic wave is generated by vibrating electric and magnetic charges. No medium is required, and the properties include, as we've said, these properties. Spectroscopy is the study of how matter interacts with light, and absorption, emission, and continuous spectrum can be used to determine an object's temperature, composition, density, velocity, distance, and rotational speed, in addition to, I'm sure, many other things for people who are smarter than me. And the speed of light is those numbers. We reviewed the history of experimental measurement of the speed of light, and we talked about time dilation, the expansion of the early universe being greater than the speed of light, and the need for GPS relativistic corrections to compensate for the effects of time dilation and gravity dilation. And in part 2, which will probably be in September or October, we're going to talk about bioluminescence, how to make a rainbow, the green flash occurring at sunset and sunrise, and about light pollution, and about any other relative topics that I come across between now and then. And I think that is it. So I'm going to stop sharing and invite questions. Any questions or thoughts?
Yeah, Craig, I'm Dave Jopi, and you said that the universe was 48 billion light years old, and they can't measure anything 48 billion light years away. How do they measure the edge of the universe?
I don't know that. I don't think anybody's measured the edge of the universe. I don't
No.
think anybody can say they've measured it.
Well, I've seen galaxies that are 38 billion light years away.
Yeah,
Yeah.
yeah. But the better the microscope, the better the telescopes get, the further away they're seeing.
Okay.
Craig,
Yeah.
I just have to inject here. Your comment about the Crookes radiometer, um, it's not really the radiation pressure that makes the veins go around in that little glass globe.
Oh,
That was
darn, it isn't.
no, that was the original thought many, many years ago. It really has to do with the heating of the black surface. That globe, the Crookes radiometer doesn't actually work if there's a perfect vacuum. It has to have some gas in it, and it's the flow
Okay.
of the gas around the edge of
Thanks.
the vein.
All right, good.
In
I
fact,
stand corrected that I'll take that out of the
yeah,
talk.
if it were the radiation pressure would actually go in the opposite direction because the photon would be being absorbed by the black, but it would be being reflected by the white, and there would be twice as much momentum transfer on the reflected side as the absorbed side, and it would go with the white going away from you rather than the black going away from you.
Ah,
So there is such a thing, obviously, as the radiation pressure, but that's not the way the Crookes radiometer works.
nice. Thank you very much for that correction. I appreciate that, Craig. Other thoughts? All right. I think we're at an end then. Thank you all so much for your attendance.
Thanks, Craig. That was good. Really
And
very
we'll
much
we'll
interesting.
post this as soon as the recording we're finishes transcribing. Thanks to everybody.
You made my head hurt, and I always appreciate that.
My head was screaming as I was rehearsing this afternoon.
Well, hopefully we'll see you Sunday at
Yes,
Ionia.
without a doubt.
Okay. Thank you again.
Take care, everybody. Very nice to be